Hello everyone, I hope you're all doing well. I'm back after a long break to continue our journey about statistics and probability. Today I'm going to show you how to code probability distributions in Python. So let's say we have a data set. When I deal with a new data set, I first go through the process of EDA and compute descriptive statistics to get a basic understanding of my data. After that, I try to determine if my data fits a certain type of probability distributions or not, like the binomial, Poisson, and normal distributions. Knowing the distribution of my data helps me decide what statistical test or machine learning model will work best for my analysis. So fortunately, Python has a great selection of function libraries for data analysis. In this video, we'll use Python to model our data with the normal distribution. Then we'll compute z-scores to find any outliers in our data. So let's get started. Imagine we're data professionals working for the Department of Education of a large nation, and we're analyzing data on the literacy rate for each district. And we already computed descriptive statistics to summarize our data. So, along with pandas, numpy, and matplotlib.pyplot, we'll also use two other Python packages, SciPy Stats and Stats Models. SciPy is an open source software you can use for solving mathematical, scientific, and technical problems. It allows you to manipulate and visualize data with a wide range of Python commands. SciPy is a module designed specifically for statistics. To start, we import the Python packages we will use in this notebook. NumPy, Pandas, Stats Models.api, and the library we will use is matplotlib.pyplot. To save time, as you can see, we name each package and library with an abbreviation. And now we want to find out if the data on literacy rate fits a specific type of probability distribution. The first step in trying to model our data with a probability distribution is to plot a histogram. This will help us to visualize the shape of our data and determine if it resembles the shape of a specific distribution. So we use matplotlib's histogram function to plot a histogram of the district literacy rate data. So we know that the overall _li column contains this data. The x-axis of our plot refers to the literacy rate of each district, and the y-axis refers to count or the number of districts. So, as you can see, the histogram shows that the distribution of our literacy rate data is bell-shaped and symmetric about the mean. Recall that the normal distribution is a continuous probability distribution that is bell-shaped and symmetrical on both sides of the mean. So here, the mean literacy rate, which is around 73%, is located in the center of the plot, and the shape of our histogram suggests that the normal distribution might be a good modeling option for our data. The next step would be checking empirical rule. We can also use Python to find out if our data follows the empirical rule. The empirical rule says that for every normal distributions, about 68% of values fall within one standard deviation of the mean, 95% fall within two standard deviations of the mean, and 99.7% fall within three standard deviations of the mean. Since the normal distribution seems like a good fit for the district literacy rate data, we can expect the empirical rule to apply relatively well. So, to do the process, first we name two new variables to store the values for the mean and standard deviation of the district literacy rate. We name our first variable mean_overall_li, and compute the mean. And we display the values of our variable by typing its name. You see the mean district literacy rate is about 73.4%. Then we name our second variable std underscore overall underscore li and compute the standard deviation. And display our value again by typing it and click on run. So the standard deviation is about 10%. Now, if our data follows the empirical rule, we can expect roughly 68% of our values to fall within one standard deviation of the mean district literacy rate of 73%. Now we can put the actual percentage of district literacy rate that falls within one standard deviation of the mean. To do this, first we name two new variables, lower underscore limit and upper underscore limit. The lower limit will be one standard deviation below the mean or the mean minus 1 times the standard deviation. The upper limit will be one standard deviation above the mean or the mean plus 1 times the standard deviation. So, to write the code for the calculations, we use our two previous variables, mean underscore overall underscore li and std underscore overall underscore li for the mean and standard deviation. Next, we add a line of code that tells the computer to decide if each value in the normal literacy column is between the lower limit and upper limit. To do this, we use the relational operators greater than or equal to and less than or equal to, and the bitwise operator and. So finally, we use the mean function to divide the number of values that are within one standard deviation of the mean by the total number of values and run the code. So the output shows that about 0.664 or 66.4% of our district literacy rates fall within one standard deviation of the mean. This is very close to 68% that the empirical rule suggests. We can also use the same code structure to determine how many values of our literacy rate values fall within 2 and 3 standard deviations of the mean. We just multiply the standard deviation by 2 or 3 instead of 1. So, as you can see, about 0.954 or 95.4% of our values fall within 2 standard deviations of the mean, and about 0.996 or 99.6% of our values fall within 3 standard deviations of the mean. So apparently all these three values of 66.4, 95.4, and 99.6% are very close to what the empirical rule suggests, roughly 68, 95, and 99.7%. At this point, it's safe to say that our data follows a normal distribution. Knowing that our data is normally distributed is useful for analysis because many statistical tests and machine learning models assume a normal distributions. Plus, when our data follows a normal distribution, we can use z-scores to measure the relative position of our values and find outliers in our data. So now let's check how to calculate z-scores in Python. As you may know, z-score is a measure of how many standard deviations below or above the population mean a data point is. A z-score is useful because it tells you where a value lies in a distribution. For example, if I tell you a literacy rate is 80%, this doesn't give you much information about where the value lies in the distributions. However, if I tell you the literacy rate has a z-score of 2, then you know that the value is 2 standard deviations above the mean. Typically, observations with the z-score smaller than a -3 or larger than +3 are outliers. These are values that lie more than 3 standard deviations below or above the mean. So to find out outliers in our data, first we create a new column called z-score that includes the z-score for each district literacy rate in our data set. And then we compute the z-scores with a function called stats.z-score. Now we write some code to identify outliers or districts with z-scores that are greater than or less than 3 standard deviations from the mean. We use the same rational operators, greater than, less than, and the bitwise operator OR. As you can see, using z-scores, we identify 2 outlying districts, district number 461 and district number 429. The literacy rates in these 2 districts are more than 3 standard deviations below the overall mean, which means that they have unusually low rates. So, important information is that the government may want to provide more funding and resources to these 2 districts in the hope of significantly improving literacy rate. So, as you found out, probability distributions are useful for modeling our data and help us determine which statistical tests use for an analysis. So that's it. Thank you so much for watching this video. I hope you liked it, and if you did, please like it and subscribe to my channel. I'll see you in the next video.